So this is the example one of this part now of verifying trig functions. Now again, we're trying this again, we're working at it again, and we just had a couple of guidelines that we just went through in the last video. So let's go back to those guidelines really quickly before we actually start this, so hopefully we can see something. But even with this, before we even start that, let me go ahead and change something because I realized I didn't write something down correctly. I left off one important piece. It should be sine squared theta, not just sine theta, because it wouldn't work out right. Right. So if you need to stop the video, go and stop the video and write that down, the problem down, and then we're going to go back to the guidelines. All right. So our guidelines, we say, okay, we have all this going on. It says number one, to choose one, work on one side of the equation and the most complicated side. So if we look here at number one, at the example one, the most complicated side is the left side or the right side? Right, it is the left side. Complicated. Oh, so complicated. Compared to this side, it's just sine squared. So we're going to work on this side and simplify this side down. Complicated side. All right, so now with that, going back to number two, it says look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. Okay, now looking at this part here, we can actually do something here to break it apart. So we have like two different fractions going on and we can simplify stuff down from there. And so here I'm going to do this. Hopefully you do remember how this works, because I'm going to pull back in an algebraic fraction here, or a rational fraction. Let's say we have y on the bottom. Oh, actually, no, let's try this. Let's do, instead of y, let's say x, because we have a cosecant and a cosecant, so let's put the same variable here. All right, so here we can break this apart, and hopefully you do remember this. You can break this apart to be two separate fractions. You might be like, whoa, wait a minute, Mr. Hall, I don't understand. I'm confused. I'm so lost. Remember, if we have a common denominator here, we can actually add the numerators together and just put it all over that denominator because it's the same denominator. Just like if it was 1/2 plus 3 halves, you would just add the numerators together, 1 plus 3, and then divide by 2, right? Because it's a common denominator of 2, which will give us 4/2, which is 2. Same thing works when we have variables with x. If it's the same denominator, you can put one of the binomial pieces terms up top, on top of that one, and then the 4 on top of that. In other words, we can say x over x, x over x, and 4 over x, and just put an addition sign in the middle because they have a common denominator. Now, with that, this right here can work the same way. Just like x is underneath both of these, we can do that same thing with cosecant. So we can do cosecant squared theta over secant, sorry, not cosecant, but secant squared theta over secant squared theta minus 1 over secant squared theta. And that's hopefully equal to sine squared theta. And just as a reminder, again, we said that you cannot automatically say that these are equal to each other and then try to cross multiply here or try to get things that cancel across the board. So you can't multiply both sides by secant squared and to get rid of the fraction. You can't do that because they're not necessarily equal to each other. We're verifying. We're trying to make sure that they are. We're trying to prove that they are. Okay. So here, if we have this going on, secant squared over secant squared, that would equal 1. Anything over itself is 1. And then here, if you remember, you have cosine theta is 1 over secant theta. And just because it's squared means it just be cosine squared. Cosine squared would be 1 over cosecant squared. So here we can use our identity, our trig identity, and change it from 1 over secant squared to cosecant squared. So 1 over cosecant. Sorry. We can, instead of saying 1 over secant squared, we can do cosine squared. Oh my gosh, I'm sorry guys. I'm like tripping right now. Tripping right now. Sorry about that. And again, this is our trig identity here. And so also, if that was like 1 over secant to the 4th power, that would just be cosine to the 4th power. That would equal that. So it doesn't really matter with the power part. It just matters the identity. Okay, so then here, the last part is just going to simplify everything down. 1 minus cosecant squared. If you remember back again from our trig identities, what trig identity has both cosine and 1 on it? And then 1 minus cosine squared theta. I don't know why I keep saying cosecant. But yes, 1 minus cosine squared theta. What is our trig function that has a 1 and a cosine squared? And hopefully everybody remembers. That is sine squared theta plus cosine squared theta equals 1. But then again, don't you remember, you can manipulate this trig identity and be able to get an answer that looks something like this. So again, if you subtract cosine squared from both sides, you would get 1 minus cosine squared, right? Right. So we get sine squared theta equals that 1 minus cosine squared theta. Bam. So can't we substitute, instead of writing 1 minus cosine squared, can't we put that in its spot? Because that's what that equals. Yes, sirree, Bob. And we have verified that they are the exact same. So this is a trig identity. Yay. Woo. Lord, we SEMA, we did it. Dun, 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 dun. All right, so we have verified it, and that's all the work we have to do. And again, look, we got it down to sines and cosines too. That just happened to happen. Okay, so again, we dealt with fractions here with like denominators. We've simplified things down. We use our trig identities. We use 2 trig identities here. We used our reciprocal identity here, and we used our Pythagorean identity here. So you might use multiple. So that's another chance to look at it. And so let's keep moving forward, get more practice with it. And when you do these videos, if you want to stop the video and try it yourself and then watch me do it later on, that's fine. Whatever you want to do to make sure you understand how to do this or have a good train of thought, because you might surprise yourself and actually be on the right track and you just want to quit and give up. Don't quit. Don't quit.